Imagine a ring of galaxies so massive it defies physics, 1,300,000,000 light-years across, floating 9 billion light-years away in the darkness. Scientists say structures this large shouldn't exist. Our universe hasn't had enough time to build them, but there it is, glowing in telescope data, impossible and real. A doctoral student found it by accident while hunting for invisible matter. She calls it the cosmic ring, and right beside it, an even stranger companion. If you're ready to question everything we know about the cosmos, take a breath. We're launching into the deep. Picture a ring floating in deep space, not a planet's ring made of ice and rock, not a nebula glowing around a dying star. This is a ring made of galaxies, thousands of them. Galaxy clusters too, bound together in a pattern that curves across the cosmos like a cosmic smile. The cosmic ring stretches 1,300,000,000 light-years from one edge to the other. To give you perspective, our entire Milky Way galaxy measures about 100,000 light-years across. The cosmic ring could fit 13,000 Milky Ways side by side along its diameter. Its total circumference measures roughly 4 billion light-years. If you tried to drive around it at the speed of light, you'd still be traveling when the universe doubled in age. This structure sits 9,200,000,000 light-years from Earth. When we look at the cosmic ring, we're seeing it as it appeared 9 billion years ago. The light reaching our telescopes today started its journey when the universe was barely half its current age. Back then, the cosmos was 1.8 times smaller than it is now, younger, denser, still forming its largest structures. But here's where things get strange. According to our current understanding of cosmology, the cosmic ring shouldn't exist at all. Scientists have calculated a theoretical size limit for cosmic structures. That limit sits at 1,200,000,000 light-years. Anything larger shouldn't have had enough time to form in the age of the universe we're observing. This structure exceeds this limit. It's too big, too organized, too perfect. The structure doesn't appear as a simple circle either. When astronomers analyzed its three-dimensional shape, they discovered something even more peculiar. The ring twists through space like a corkscrew. Imagine a spring from inside a pen, but each coil contains billions of galaxies, and by pure chance, this cosmic spring happens to be oriented face-on toward Earth. We're looking straight down its barrel. The discovery happened in 2024, announced at the 243rd meeting of the American Astronomical Society. Scientists presented it as one of the most significant cosmological findings in recent years. Why? Because it joins a growing list of structures that challenge our fundamental assumptions about how the universe works. This structure appears in the constellation Boötis, named after a herdsman from Greek mythology. Ancient stargazers saw a man chasing bears across the night sky. They had no idea that billions of light-years beyond those stars, galaxies were arranging themselves into impossible patterns. Most cosmic structures show some irregularity, some chaos in their formation. This structure displays an almost perfect symmetry. Its shape remains consistent as you trace around its circumference. Some regions contain denser concentrations of galaxies than others, but the overall pattern holds. It's as if something drew a circle in space using galaxy clusters as paint. The question burning in every cosmologist's mind: what force could create something this organized on such a massive scale? The discovery sends ripples through the scientific community. Cosmologists gather at conferences, debating what it means. Graduate students stay late in labs, running new simulations. Telescopes around the world turn toward Boötis, hoping to find more clues hidden in that patch of sky. Alexia Lopez never set out to revolutionize cosmology. She was a doctoral student at the University of Central Lancashire, working on her doctoral research. Her focus? Large-scale structures in the universe. She wanted to understand how galaxies cluster together across cosmic distances. Standard research, nothing that would make headlines. Lopez used data from the Sloan Digital Sky Survey, a massive astronomical project that has mapped millions of celestial objects. The survey operates telescopes in New Mexico and Chile, scanning the sky continuously, collecting light from the most distant corners of the observable universe. Over the years, it has created one of the most comprehensive three-dimensional maps of galaxies ever assembled. But Lopez wasn't looking at galaxies directly. She was hunting for something more subtle, something invisible. She focused on magnesium absorption lines in the spectra of distant quasars. This technique represents a relatively new approach to finding large-scale structures. Instead of spotting galaxies themselves, she tracked the shadows they cast in light passing through them. Here's how it works. Quasars are extraordinarily bright objects powered by supermassive black holes consuming matter. They shine so brilliantly that we can detect them across billions of light years. As their light travels toward Earth, it passes through clouds of gas surrounding galaxies. These gas clouds contain magnesium atoms that absorb specific wavelengths of light. By studying which wavelengths get absorbed and how much, astronomers can map where matter exists between us and the quasar. Lopez studied approximately 40,000 quasars. She examined their spectra, looking for patterns in the magnesium absorption. She was essentially using quasars as cosmic flashlights, illuminating invisible matter along the line of sight. The magnesium signatures told her where gas clouds sat in space and how far away they were. Then she noticed something odd. The absorption patterns weren't random. They formed a structure. A hint of something large began emerging from the data. She remembers going to her doctoral advisor, Roger Clowes, and saying something like, "Look at this." The pattern suggested galaxies and galaxy clusters arranged in an arc across the sky. But was it real, or was it just a statistical fluke? The human brain excels at finding patterns even in random noise. Scientists call this pareidolia. We see faces in clouds, animals in rock formations, constellations in scattered stars. Clowes suggested rigorous statistical analysis before making any claims. Lopez applied 3 different statistical tests to the data: single linkage hierarchical clustering, the Cusick-Edwards test, power spectrum analysis. Each method approached the question from a different angle, examining whether the pattern showed genuine cosmic structure or mere coincidence. The results came back: approximately 4 sigma confidence for clustering, 3 sigma for the Cusick-Edwards test, nearly 5 sigma for power spectrum analysis. In statistics, 5 sigma means less than 1 in 3.5 million chance of being wrong. The structure was real. Lopez had found something extraordinary, but she had no idea just how extraordinary it would become. The statistical rigor matters immensely in astronomy. False positives plague the field. Researchers occasionally announce discoveries that later prove illusory. Lopez and Clowes knew they needed ironclad evidence before going public. They checked and rechecked their analysis, looking for any possible error or bias that could explain the pattern. Light carries information. Every photon that reaches Earth has traveled through space, bouncing off or passing through matter along the way. By the time it hits our telescopes, it tells a story about everything it encountered during its journey. Scientists have learned to read these stories written in light. When light passes through a cloud of gas, atoms in that gas absorb specific wavelengths. Each element absorbs its own unique pattern, like a fingerprint. Hydrogen absorbs certain wavelengths. Helium absorbs others. Magnesium has its own signature. By examining which wavelengths are missing from light that reaches us, we can determine what elements the light passed through and in what quantities. Magnesium works particularly well for detecting large-scale structures. It exists abundantly in the gas clouds surrounding galaxies. When a quasar's light passes through these clouds, singly ionized magnesium atoms absorb specific frequencies in the ultraviolet range. Astronomers call this MGII, absorption. The strength of the absorption tells us how much magnesium the light encountered. The wavelength shift tells us how far away the gas cloud sits. This technique opens a window that direct observation cannot. We can't see the gas clouds themselves. They don't emit enough light. But we can see their shadows cast across the brilliant backgrounds of quasars. It's like seeing a ghost by the footprints it leaves, rather than seeing the ghost itself. Lopez's approach represented something novel in cosmology. Previous searches for large-scale structures relied on directly observing galaxies and mapping their positions. This works well for relatively nearby structures where galaxies appear bright enough to catalogue individually. But for structures at extreme distances, direct observation becomes challenging. The galaxies appear too faint, too small, too numerous to map efficiently. Using magnesium absorption sidesteps this problem. Quasars are bright enough to observe even at enormous distances. Their light provides a probe that can detect matter we'd otherwise miss entirely. The method works particularly well for finding structures at redshifts between 0.45 and 2.25. This range corresponds to looking back roughly 4 billion to 10 billion years into cosmic history. This formation sits at a redshift of approximately 0.8. This means the light we're seeing left those galaxies when the universe was significantly younger. The expansion of space has stretched that light's wavelength by a factor of 1.8. What started as ultraviolet and visible light has shifted into the near-infrared and red portions of the spectrum. When Lopez mapped the magnesium absorption patterns, the structure emerged like invisible ink, becoming visible under special light. The data points clustered in a distinctive arc shape initially. Further analysis revealed the full ring pattern. The gas clouds traced out galaxy positions across billions of light-years of space. But magnesium absorption shows us more than just location. It reveals how matter distributes itself on cosmic scales. The density of absorption indicates where galaxy clusters concentrate most heavily. The gaps between absorption regions show where cosmic voids exist. Together, these patterns paint a picture of the universe's large-scale structure, and that picture shows something our theories didn't predict. Let's talk about cosmic speed limits, not the speed of light, a different kind of limit entirely, a limit on how large structures in the universe can grow. After the Big Bang, matter spread outward in all directions. Tiny quantum fluctuations created slight differences in density. Some regions had fractionally more matter than others. Gravity began pulling matter toward these denser regions. Over millions of years, these small differences grew into larger ones. Matter clumped together. Stars formed. Galaxies emerged. Galaxy clusters appeared. But this process takes time. Gravity works slowly on cosmic scales. To pull together a galaxy cluster, you need millions of years. To create a supercluster, you need hundreds of millions. To organize multiple superclusters into a coherent structure, you need billions of years. The universe has existed for 13.8 billion years. That puts a natural limit on how large structures could have grown. Cosmologists calculated this limit based on our understanding of gravity, dark matter, and cosmic expansion. They determined that structures shouldn't exceed approximately 1,200,000,000 light-years across. Anything larger wouldn't have had enough time to form through gravitational collapse. The universe's expansion works against structure formation, pulling space apart even as gravity tries to pull matter together. At scales larger than 1.2 billion light-years, expansion should win. This formation measures 1,300,000,000 light-years in diameter. It exceeds the theoretical limit by 100 million light-years. That might not sound like much, but in cosmology, it's massive. We're talking about a structure roughly 8% too large to exist according to our current models. But the diameter tells only part of the story. The circumference measures approximately 4 billion light-years. If you tried to trace the entire ring, traveling at the speed of light, the journey would take 4 billion years. By the time you completed the loop, the universe would be nearly 30% older than it is now. The Big Ring's mass staggers the imagination. While exact calculations remain uncertain, estimates suggest it contains the mass of millions of galaxy clusters. Each cluster itself contains hundreds or thousands of galaxies. Each galaxy contains billions of stars. The total stellar mass likely exceeds 10 to the power of 15 times our star's mass. The structure doesn't appear as a thin ring either. It has thickness, depth. The ring extends roughly 650 million light-years in width. Galaxies don't line up in a perfect one-dimensional curve. They fill a tube-like volume that sweeps through space in a ring pattern. Scientists have discovered other large structures before: the Sloan Great Wall, the Hercules Corona Borealis Great Wall. Each one pushed the boundaries of what we thought possible. But the Big Ring combines enormous size with striking geometric regularity. 3 times the theoretical size limit, formed when the universe was half its current age, displaying near-perfect circular symmetry. Every aspect of the Big Ring seems designed to challenge our understanding of cosmic structure formation, and we're only beginning to understand what it means. The Big Ring doesn't just violate size limits. It challenges something even more fundamental: the cosmological principle. This principle states 2 simple ideas. First, homogeneity. The universe looks roughly the same everywhere. Second, isotropy. The universe looks roughly the same in every direction. There should be no special places in the cosmos, no preferred directions, no cosmic landmarks visible across billions of light-years. These assumptions underpin our entire standard model of cosmology. They let us apply the laws of physics equally across all of space. They simplify the mathematics of cosmic evolution enormously. Without the cosmological principle, cosmology becomes vastly more complicated. But the principle only applies at large enough scales. Zoom in close, and the universe looks anything but smooth. Earth sits in a solar system. Our solar system sits in a galaxy. Our galaxy sits in a local group. The local group sits in a larger supercluster. These are all structures, all departures from perfect homogeneity. But cosmologists argue that if you zoom out far enough, these lumps smooth out into an even distribution. The question is, how far is far enough? Early estimates suggested that above approximately 300 million light-years, the universe should appear homogeneous. Later calculations pushed that scale up to 1 billion light-years or so. Above this scale, you shouldn't see coherent structures anymore. Matter should distribute itself evenly when you average across regions of this size. The Big Ring smashes through this scale. It measures 1.3 billion light-years across. Its circumference spans 4 billion light-years. A massive, organized structure at scales where such structures shouldn't exist. Imagine you're told that if you zoom out far enough on a map of Earth, it should look perfectly smooth. No mountains, no valleys, just a uniform sphere. Then someone shows you a mountain range that circles the entire planet and rises above the atmosphere. That's roughly the scale of violation we're seeing with the Big Ring. The structure's shape makes matters worse. Random density fluctuations might occasionally create slightly larger structures than expected. Statistical outliers happen. But random fluctuations don't create near-perfect ring shapes. They don't create symmetrical arcs. They don't organize matter into geometric patterns. The Big Ring's corkscrew geometry particularly puzzles astronomers. The structure twists through 3-dimensional space like a helix or a spring. Imagine a slinky toy. Now imagine each coil contains galaxy clusters instead of metal wire, and imagine the entire thing stretches across more than 1 billion light-years. That's the Big Ring. The fact that we see it face-on adds another layer of strangeness. We happen to be positioned in the universe such that we're looking straight down the axis of this cosmic corkscrew. Pure coincidence? Or does this orientation tell us something about the structure's nature? The cosmological principle assumes the universe contains no special positions, but the Big Ring creates a special position, its center. The ring has a middle, an inside, and an outside, an axis of symmetry. These are features. landmarks. Exactly what the cosmological principle says shouldn't exist at these scales. Something is breaking the rules we thought governed cosmic structure. The question is, what? Let's step back. Why do cosmologists believe in the cosmological principle? It's not just convenient mathematics. The principle has strong observational support. The cosmic microwave background provides the clearest evidence. This radiation fills the entire observable universe. It's the afterglow of the Big Bang itself, light that has been traveling through space for 13.8 billion years. When we measure its temperature in different directions, we find it remarkably uniform. The temperature averages 2.725 degrees above absolute zero everywhere we look. Small fluctuations exist, yes. The temperature varies by about 1 part in 100,000 across the sky. These tiny variations represent the seeds that eventually grew into galaxies and galaxy clusters. But overall, the cosmic microwave background shows stunning homogeneity. As the universe aged, gravity amplified those tiny density differences. Slightly denser regions attracted more matter. Over billions of years, this created the cosmic web we see today. Long filaments of galaxies separated by vast voids. But even this web-like structure should look statistically similar everywhere if you zoom out far enough. Surveys of galaxy distribution support this idea at moderate scales. When astronomers map millions of galaxies and analyze their distribution, they find that the universe does appear roughly homogeneous above certain size scales. But recent discoveries challenge this picture. The Big Ring represents just one example. The Sloan Great Wall stretches 1.37 billion light-years across. The huge large quasar group spans approximately 4 billion light-years. The Hercules Corona Borealis Great Wall might exceed 10 billion light-years in length, though its existence remains controversial. Each discovery pushes the boundaries of what the cosmological principle allows. Defenders argue that these structures represent statistical flukes. In a universe large enough, even unlikely events happen occasionally. Find enough galaxy clusters, you'll occasionally see them line up in unexpected ways. But how many outliers can a theory tolerate before it breaks? The Big Ring is now the 7th ultra-large structure discovered that appears to violate the expected size limits. At what point do we stop calling them anomalies and start questioning the principle itself? Some cosmologists suggest we're experiencing observer bias. We notice large structures because they're unusual and interesting. Meanwhile, we ignore the countless regions of space that look exactly as homogeneous as the theory predicts. Others argue the violations are real and significant. Our observable universe only shows us a limited sample of cosmic structure. We see a sphere roughly 93 billion light-years across. If ultra-large structures exist at scales comparable to our observable universe, we might only see fragments of them. There's also the question of cosmic time. The Big Ring exists 9 billion light-years away. We see it as it was 9 billion years ago. Perhaps structures in the early universe were legitimately more clumpy, more organized, more prone to forming geometric patterns. Or perhaps our fundamental assumptions about cosmic structure formation need revision. Perhaps gravity doesn't work exactly as we think at the largest scales. Perhaps dark matter behaves differently than our models predict. The Big Ring doesn't answer these questions, but it forces us to ask them. Here's where the story takes an even stranger turn. The Big Ring isn't alone. In 2021, 3 years before discovering the Big Ring, Alexia Lopez made another remarkable finding. She discovered the giant arc on the sky. This structure stretches approximately 3.3 billion light-years across space. It curves through the cosmos in a massive arc shape, like a cosmic bow or crescent. The giant arc uses the same type of structure as the Big Ring: galaxies, galaxy clusters, gas clouds, and dust arranged in a coherent pattern. Lopez found it using the same method, analyzing magnesium absorption lines in quasar spectra. It sits at the same distance from Earth, roughly 9.2 billion light-years away. And here's the truly remarkable part. The giant arc and the big ring exist in the same region of space. When Lopez mapped both structures, she found them separated by only 12 degrees on the sky. Your fist held at arm's length covers roughly 10 degrees. These two enormous structures sit close enough together that you could cover both with 2 fists. Both structures appear near the constellation Boötes. Both exist at redshift 0.8. Both formed billions of years ago in the same cosmic epoch. The probability of finding 2 such massive structures in close proximity by pure chance is extraordinarily low. The giant arc actually exceeds the theoretical size limit even more dramatically than the Big Ring. It measures 3.3 billion light-years across. That's nearly 3 times the maximum size cosmologists calculated. If the Big Ring seems impossible, the giant arc seems triply impossible. Lopez's statistical analysis showed approximately 4.5 sigma significance. Like the Big Ring, the giant arc passed rigorous statistical scrutiny. It wasn't an artifact of the data or a trick of perception. The structure appears almost symmetrical. It forms a smooth curve across the sky, though not as geometrically perfect as the ring shape of its companion. Some astronomers have compared it to a smile or a crescent moon, but scaled up to inconceivable proportions. When you examine the 3-dimensional structure, it shows as an enormous curved sheet of galaxy clusters. Each cluster contains hundreds or thousands of individual galaxies. The arc sweeps through space in a gentle curve that spans billions of light-years. The giant arc's discovery in 2021 already challenged cosmology. Scientists struggled to explain how such a massive structure could form. They proposed various mechanisms. Perhaps cosmic strings passed through this region of space. Perhaps our understanding of structure formation needed updating. Then Lopez discovered the Big Ring in the same neighborhood. Suddenly, explaining one massive structure wasn't enough. Now cosmologists had to explain 2 massive structures in close proximity. The challenge multiplied. The proximity raises an obvious question. Are these structures related? Did the same process create both? Could they actually be parts of a single, even larger structure that we're seeing from an angle that makes it look like 2 separate objects? This dual discovery changes everything. Finding one impossible structure could be dismissed as a fluke, an outlier that barely qualifies as statistically significant. Finding 2 in the same location demands explanation. The universe seems to be telling us something through these structures, though we haven't yet learned to decode the message. 9.2 billion light-years away, same distance, same cosmic time, same region of sky. The overlap between the Big Ring and the giant arc goes beyond coincidence. When light travels billions of years to reach us, looking out into space means looking back in time. The light from these structures started its journey when the universe was only about half its current age. These structures existed when the cosmos measured approximately 6.9 billion years old. Earth formed about 4.5 billion years ago. The Big Ring and giant arc were already ancient structures before our planet even existed. At that cosmic epoch, the universe was denser than today. Space had expanded less. Galaxies sat closer together. The cosmic web of matter appeared tighter, more concentrated. This was still relatively early in the universe's history, but even accounting for the younger, denser universe, structures the size of the Big Ring and giant arc shouldn't have had time to form. Gravity works slowly. It takes hundreds of millions of years to pull together a galaxy cluster. It should take billions of years to organize multiple clusters into coherent structures spanning billions of light years. The universe, at age 6.9 billion years, had existed for only half as long as today. That gave structure formation processes only half as much time to work. Yet, somehow, these 2 enormous structures had already formed, already achieved their current sizes, already organized themselves into geometric patterns. The spatial proximity adds another layer of mystery. In three-dimensional space, they exist in the same cosmic neighborhood. Think of the universe as a vast ocean. The Big Ring and Giant Arc are both in the same small region, at the same depth, formed at the same time. Cosmologists call this region of space around redshift 0.8, and in the direction of violates, a special place. It contains not one, but two structures that challenge our understanding. This raises uncomfortable questions. Is this region actually special? Or do similar structures exist elsewhere in the universe, waiting to be discovered? If this region is genuinely special, that directly violates the cosmological principle. The universe shouldn't have special places. Finding two ultra-large structures in the same neighborhood suggests that matter distribution might not be as homogeneous as we thought. If similar structures exist elsewhere, why haven't we found more? Lopez's technique seems effective. She found two using magnesium absorption analysis. If ultra-large structures were common, shouldn't we be finding them throughout our sky surveys? Perhaps we are finding them, and we just don't recognize them yet. The Big Ring and Giant Arc only became visible through careful analysis of absorption patterns. You can't see the forest if you're standing among the trees. Or perhaps there's something unique about this region that allowed these structures to form. Some local density enhancement in the early universe. Some interaction between dark matter halos that doesn't happen elsewhere. The fact that both structures appear at the same distance from Earth also matters. We can study them at the same level of detail. We can compare their properties directly. This provides a unique laboratory for testing theories about ultra-large structure formation. But it also deepens the mystery. Why here? Why now? Why these two structures together? Look at a map showing both structures. The Big Ring curves through space in one direction. The Giant Arc sweeps through in another. They don't touch, but they're close. Cosmologically speaking, they're neighbors. Some astronomers wonder whether we're seeing two separate structures or two parts of one megastructure. Imagine looking at a giant sculpture from a specific angle. From your viewpoint, it might appear as two distinct objects. Move to a different position, and you'd see how they connect. We're stuck with one viewpoint. Earth's position in space. We can't fly around these structures to view them from different angles. We see them from 9 billion light-years away, frozen in the configuration they held 9 billion years ago. But consider this possibility. The Big Ring forms a circle in three-dimensional space, oriented face-on toward us. The Giant Arc curves through space nearby. What if they're actually connected? What if they're both edges of some larger structure that we can't fully perceive from our vantage point? Think about looking at a coffee cup. From directly above, you see a circle. From the side, you see a curved line. Both views show the same object from different angles. Could the Big Ring and Giant Arc represent different aspects of a single cosmic structure? If true, this combined structure would dwarf anything we've ever discovered. A structure that incorporated both would measure larger still. We'd be looking at something comparable in scale to a significant fraction of the observable universe itself. Alexia Lopez has suggested this possibility. Finding two ultra-large structures in such close configuration raises the likelihood that they form an even more extraordinary cosmological system together. The odds of two unrelated structures appearing so close seem vanishingly small. This interpretation makes the challenge to the cosmological principle even more severe. A single structure spanning multiple billions of light-years, organized into complex geometry, existing in the early universe when it shouldn't have had time to form. But other interpretations exist. Perhaps the Big Ring and Giant Arc formed independently through similar processes. Perhaps the same conditions that created one also created the other. They could be siblings rather than parts of a whole. Or perhaps their proximity is gravitational. Maybe the Giant Arc's gravity influenced the formation of the Big Ring, or vice versa. even separated by hundreds of millions of light years. These structures contain enough mass to exert gravitational influence on each other. Current data doesn't definitively answer whether we're seeing one structure or two. Lopez and her colleagues continue analyzing the observations. They're looking for velocity patterns in the galaxies, examining how the structures move relative to each other. If the Big Ring and giant arc move together, sharing similar velocities, that would suggest they're dynamically connected. If they move independently, that would support the interpretation of two separate structures. Either way, the implications are profound. Two structures challenge cosmology. One megastructure challenges it even more dramatically. We're looking at evidence that our current models of the universe are incomplete at best, fundamentally wrong at worst. When scientists discover something that shouldn't exist, they search for explanations. The Big Ring demands an explanation. One possibility involves baryonic acoustic oscillations. Let's rewind to shortly after the Big Bang. The universe was hot, dense, and filled with plasma. Photons and matter mixed together intimately. Pressure waves rippled through this primordial plasma like sound waves through air. Then, approximately 380,000 years after the Big Bang, the universe cooled enough for atoms to form, photons decoupled from matter. The pressure waves froze in place, leaving an imprint in the distribution of matter. This imprint shows up as a characteristic scale in how galaxies cluster together today. Baryonic acoustic oscillations create a preferred separation distance between galaxy clusters. When we map galaxies in the modern universe, we find they're more likely to be separated by approximately 490 million light-years than by other distances. These oscillations should appear as roughly spherical shells in the arrangement of galaxies. Imagine dropping a pebble in a pond. Ripples spread outward in circles. Baryonic acoustic oscillations work similarly, except in 3 dimensions. Could the Big Ring represent a baryonic acoustic oscillation? It's ring-shaped, which could correspond to a spherical shell viewed from within or near its surface. It would provide a natural explanation rooted in established physics. But detailed analysis reveals problems. First, the Big Ring measures too large. Baryonic acoustic oscillations create features at approximately 490 million light-year scales. The Big Ring spans 1.3 billion light-years. That's nearly 3 times too big. Second, baryonic acoustic oscillations should appear as statistical features, not as individual coherent structures. When we analyze millions of galaxies, we find a slight preference for certain separation distances. But individual galaxy clusters don't organize themselves into perfect circles. The signal shows up only in statistical averages. The Big Ring appears as a distinct individual structure with clear geometric organization. It's not a statistical tendency. It's an actual ring of galaxies and galaxy clusters arranged in space. That doesn't match how baryonic acoustic oscillations manifest. Third, baryonic acoustic oscillations should create spherical patterns. The Big Ring isn't spherical. Its 3-dimensional structure forms a corkscrew or helix. This geometry doesn't match what we'd expect from primordial sound waves frozen into the matter distribution. Alexia Lopez and her colleagues examined whether the Big Ring could be explained as a baryonic acoustic oscillation. Their conclusion? Probably not. The size is wrong. The shape is wrong. The coherence is wrong. While baryonic acoustic oscillations definitely exist and influence cosmic structure, they don't explain the Big Ring. So, if not baryonic acoustic oscillations, what? Scientists have proposed alternative explanations, each with its own challenges. But what comes next grows even stranger than sound waves from the infant universe. The rejection of baryonic acoustic oscillations as an explanation forces scientists back to the drawing board. If conventional physics can't account for the Big Ring, they must consider more exotic possibilities. The search for answers pushes cosmology into uncharted theoretical territory, where established models give way to speculation and new ideas. Scientists don't dismiss theories lightly. They test every possibility, run calculations, check the math. When baryonic acoustic oscillations failed to explain the Big Ring, researchers moved to other hypotheses. But each explanation ran into the same fundamental problem: the numbers don't work. Consider the timeline. The Big Ring exists as we see it 9 billion years ago. The universe at that point had existed for only about 7 billion years since the Big Bang. 7 billion years sounds like a long time. In cosmic terms, it's barely enough time for structure formation. Here's how structure formation typically works. Tiny density fluctuations in the early universe start attracting matter through gravity. A region with slightly more matter pulls in more matter from surrounding space. This process accelerates over time. Eventually, it collapses into a galaxy. Multiple galaxies cluster together. Clusters join into superclusters. Each step requires time. Hundreds of millions of years minimum, often billions. The larger the structure, the more time it needs. Gravity must overcome the expansion of space, pulling matter together against the outward motion of cosmic expansion. Think of it like trying to herd cats across a field that's actively stretching. The field grows larger while you work. The cats you've already gathered keep getting farther apart because the ground between them expands. You're fighting against the expansion just to maintain the group you've assembled. Dark matter helps this process. Its gravitational pull assists in gathering normal matter into structures. Dark matter halos form first, creating gravitational wells that attract gas and dust. But even with dark matter's help, there are limits to how fast structures can grow. The Big Ring exceeds those limits. It's too massive, too organized, too geometrically precise for the time available. If you run simulations of structure formation, starting from the conditions we observe in the early universe, you don't get big rings appearing at redshift 0.8. The shape presents another mathematical challenge. Random gravitational collapse doesn't create rings. It creates irregular blobs, filaments, sheets. The cosmic web shows this clearly. Galaxies arrange themselves along filaments, connecting massive clusters. Ring shapes require special conditions. Symmetry. Some organizing principle beyond simple gravitational collapse. In small-scale systems, we understand how rings form. Saturn's rings formed from a moon torn apart by tidal forces. But the Big Ring doesn't have an obvious central mass creating tidal forces. The corkscrew geometry adds yet another layer of strangeness. Helical structures appear in nature through specific physical processes, but a corkscrew of galaxy clusters spanning billions of light years. No known mechanism produces that. Cosmologists have run computer simulations trying to reproduce the Big Ring. They start with initial conditions matching what we observe in the cosmic microwave background. They let gravity and dark matter interact over billions of years of simulated time. They watch structures form and grow. But the simulations don't produce anything resembling the Big Ring. The math doesn't support its existence. Yet there it is, visible in the data, undeniably real. This mathematical crisis strikes at the heart of modern cosmology. For decades, scientists believed they understood structure formation well enough to predict what should and shouldn't exist. The Big Ring undermines that confidence, suggesting our grasp of cosmic evolution remains incomplete despite all our technological advances and theoretical sophistication. Conventional explanations fail. Time to consider unconventional ones. Enter cosmic strings. These aren't strings like you'd find in a hardware store. Cosmic strings represent hypothetical topological defects in the fabric of space-time itself. Imagine the universe as a crystal forming from liquid as it cools. Sometimes the crystal develops flaws where the molecular structure doesn't quite line up correctly. Cosmic strings would be similar defects in space-time, formed during the first fraction of a second after the Big Bang. As the universe cooled and underwent phase transitions, regions of space might have locked into slightly different configurations. The boundaries between these regions could form long, incredibly thin lines of concentrated energy. If they exist, these strings would be mind-bogglingly dense. A cosmic string thinner than a proton could have the mass of a mountain range. Some theoretical models suggest cosmic strings could stretch across the entire observable universe. The gravity of a cosmic string doesn't pull inward like a star or black hole. Instead, it creates a distinctive cone-shaped distortion of space-time. Matter on one side gets deflected in one direction. Matter on the other side gets deflected the opposite way. If a cosmic string passed through a region filled with galaxies, it could organize those galaxies into unusual patterns. Could a cosmic string have created the Big Ring? The idea has some appeal. A loop of cosmic string could create a ring-shaped gravitational influence. Galaxies encountering this influence would be pulled into alignment with the string's geometry. Nobel Prize winner Jim Peebles recently suggested that cosmic strings might play a role in creating some of the peculiarities we observe in large-scale structure. His endorsement lends credibility to an otherwise speculative idea. But cosmic strings remain purely hypothetical. We've never directly detected one. We have theoretical reasons to believe they might exist, based on certain models of the very early universe. But we have no observational confirmation. Even if cosmic strings exist, do they work the right way to create the Big Ring? The string would need to be curved into a loop, positioned just right, with just the right mass and tension. The conditions seem highly specific. And cosmic strings still don't explain the giant arc. If a loop of cosmic string created the Big Ring, what created the giant arc nearby? Another cosmic string? Two cosmic strings in the same region of space? Some versions of string theory predict that cosmic strings should be common in the universe. Others predict they should be extremely rare or might not exist at all. The theoretical landscape remains uncertain. Yet the idea persists because conventional physics offers no better alternatives. When faced with observations that violate our understanding of how the universe works, scientists must either expand that understanding or question the observations themselves. The Big Ring's reality seems solid, so perhaps our understanding needs expansion. The cosmic string hypothesis represents a desperate reach for explanation. Scientists generally prefer conventional answers over exotic ones. But when conventional physics fails repeatedly, exotic physics becomes necessary. The Big Ring might be forcing cosmology to embrace ideas once relegated to the fringes of respectability. Let's push deeper into the cosmic string hypothesis. If these objects exist, how would they actually organize galaxies into rings? Imagine a massive cosmic string loop floating in space during the early universe. The universe at that time was much smaller, much denser. Matter filled space more evenly. Dark matter halos were just beginning to form. The cosmic string creates a gravitational influence, not a simple pull toward a center point. Instead, the string bends space-time around itself in a cone shape. Light passing on one side gets deflected one way. Light passing the other side gets deflected the opposite way. But the string also influences matter. Gas clouds encountering the string's gravitational field get compressed along certain directions, stretched along others. The compression could trigger star formation. Regions near the string might form stars and galaxies faster than regions farther away. Over millions of years, this effect could organize matter along the path of the string. Think of iron filings aligning themselves with a magnetic field. The cosmic string's gravity provides the organizing principle, and galaxies arrange themselves in response. The string wouldn't need to remain in place forever. It could pass through the region early in cosmic history, leaving behind an imprint in the matter distribution. Like a boat creating a wake that persists after the boat passes, the cosmic string could organize matter into patterns that remain even after the string itself moves on. Cosmic strings also interact with each other. When two strings cross, they can exchange ends in a process called reconnection. This creates new loops, new configurations, new gravitational influences. A network of cosmic strings passing through the early universe could create multiple unusual structures in the same region. This might explain why both the Big Ring and giant arc appear in the same cosmic neighborhood. Some theoretical models suggest cosmic strings should oscillate. They'd vibrate like plucked guitar strings, sending out gravitational waves. These oscillations could create time-varying gravitational fields that influence structure formation in complex ways. But here's the challenge. Cosmic strings, if they exist, should create many observable effects beyond just organizing galaxies. They should produce distinctive patterns in the cosmic microwave background. They should create characteristic gravitational wave signatures. They should cause double images of distant quasars. We don't see convincing evidence for these effects yet. Some researchers claim to have found hints of cosmic string effects in cosmic microwave background data. Others dispute these claims. Gravitational wave detectors like LIGO and Virgo listen for signals from cosmic strings. They haven't found convincing evidence yet. This places limits on how common and how massive cosmic strings can be. This creates a dilemma. To explain the Big Ring through cosmic strings, the strings need to be massive enough to organize billions of galaxies. But they also need to be subtle enough to have avoided detection in all our other observations. That's a narrow window of possibility. Even advocates of cosmic string models admit the theory faces serious challenges. The strings need very specific properties to create the Big Ring while avoiding detection in other observations. This fine-tuning troubles many cosmologists, who prefer explanations that work naturally without requiring precisely calibrated parameters. The Big Ring isn't alone. The giant arc isn't alone. They join a growing family of cosmic oddities that refuse to follow the rules. The Sloan Great Wall. Discovered in 2003, this structure spans approximately 1.37 billion light-years. It consists of a massive concentration of galaxies forming a wall-like pattern through space. At the time of discovery, it was the largest known structure in the universe. The huge LQG, the Huge Large Quasar Group, contains 73 quasars spread across approximately 4 billion light-years of space. Quasars don't randomly cluster at these scales. Their distribution should be essentially random above certain size limits. The huge LQG violates those expectations. The Hercules Corona Borealis Great Wall. This monster might stretch 10 billion light-years across space. If real, it dwarfs everything else. Some astronomers question whether it represents a genuine structure or a statistical artifact. But if it exists as a real structure, it obliterates theoretical size limits. The giant GRB ring. Gamma-ray bursts distributed in a ring pattern spanning roughly 5 billion light-years. These bursts mark the deaths of massive stars. They shouldn't organize themselves into rings across such vast distances. The Boss Great Wall. Discovered in data from the Baryon Oscillation Spectroscopic Survey, this structure extends approximately 1 billion light-years. Another entry in the catalogue of two large structures. The Claus-Campusano LQG. One of the earlier discoveries of an ultra-large quasar group stretching approximately 2 billion light-years. Found in 1991, it was among the first observations suggesting that the largest structures might exceed theoretical expectations. Now add the Big Ring and giant arc. 7 confirmed ultra-large structures, possibly 8 if the Hercules Corona Borealis Great Wall proves real. Each one challenges the theoretical size limit of 1.2 billion light-years. You might wonder, are these discoveries increasing because structures like this are common, or because we're getting better at finding them? Both factors play a role. Modern telescopes see deeper into space. New techniques reveal structures invisible to older methods, but improved detection doesn't fully explain the trend. If the universe were truly homogeneous at large scales, we shouldn't find these structures no matter how good our telescopes become. The fact that we keep discovering them suggests they genuinely exist. Each discovery makes the others more significant. One ultra-large structure could be a statistical fluke. 2 could be coincidence. 3 starts looking like a pattern. 7 suggests something fundamental about our cosmological models needs revision. The structures show diversity too. Some are walls, some are rings, some are filaments. They appear at different distances, different epochs, different regions of sky. This variety suggests multiple formation mechanisms might be at work. The accumulation of ultra-large structures creates a crisis in cosmology. Each individual discovery could potentially be explained away, but collectively, they paint a picture of a universe that behaves differently than our theories predict. The question shifts from explaining individual anomalies to explaining why anomalies keep appearing. Time becomes the critical constraint. The Big Ring exists at redshift 0.8. Light reaching us today from that structure left it 9 billion years ago. The universe at that moment had existed for approximately 7 billion years since the Big Bang. 7 billion years. Long enough for stars to form, live, and die. Long enough for multiple generations of stars to enrich the cosmos with heavy elements. Long enough for galaxies to develop and merge. Long enough for many things. But long enough to build the Big Ring? Let's trace the timeline backward. The Big Bang occurs at time 0. The first atoms form after 380,000 years. The cosmic dark ages follow. No stars yet, just clouds of hydrogen and helium spreading through expanding space. The first stars ignite perhaps 150 million years after the Big Bang. These population 3 stars live fast and die young, exploding as supernovae, creating the first heavy elements. The first galaxies appear between 200 million and 500 million years after the Big Bang. Small, irregular, actively forming stars. These proto-galaxies merge together, building larger galaxies. Galaxy clusters emerge later still. You need multiple galaxies to cluster together first. This requires perhaps 1 billion years after the Big Bang. Early clusters appear small, loosely bound. They grow over time through mergers. Superclusters form last. These represent the largest gravitationally bound structures in the universe. Formation timescales stretch into multiple billions of years. Current estimates suggest the largest superclusters in today's universe required most of cosmic history to achieve their current sizes. The Big Ring spans scales larger than superclusters. It contains multiple galaxy clusters arranged in a ring pattern across 1.3 billion light-years. For this structure to exist at redshift 0.8, it must have formed within the first 7 billion years of cosmic history. Computer simulations of structure formation start with conditions matching the cosmic microwave background. They evolve forward in time, letting gravity and dark matter shape the matter distribution. These simulations successfully reproduce many features of the observed universe. Galaxy clusters appear at the right times. The cosmic web emerges naturally, but the simulations don't produce big rings. They don't generate giant arcs. The largest structures in simulations at redshift 0.8 measure smaller than observations show in reality. Something is missing from the simulations. Perhaps dark matter behaves differently than we think. Our simulations assume dark matter is cold, meaning it moves slowly. Cold dark matter models work well for most structure formation, but maybe dark matter has properties we haven't accounted for. Or perhaps the early universe was lumpier than we think. The cosmic microwave background shows tiny temperature fluctuations. These represent density variations in the early universe. But what if some regions were significantly denser than the average? The cosmic microwave background might not reveal these ultra-dense patches if they were rare enough. The timeline constraint becomes even more severe when you consider the giant arc alongside the Big Ring. Both structures exist at the same cosmic epoch, suggesting whatever process created them operated efficiently in the early universe. Traditional structure formation timescales simply don't accommodate such rapid assembly of billion light-year structures. The construction challenge staggers the imagination. Building a structure spanning 1,300,000,000 light-years requires moving unimaginable amounts of matter across unimaginable distances. Start with a single galaxy cluster. A typical cluster contains hundreds of galaxies. Each galaxy contains hundreds of billions of stars. Add it all up, and a galaxy cluster masses about 100 trillion to 1 quadrillion times our star's mass. The dark matter halo surrounding the cluster adds 5 to 10 times more mass still. The Big Ring contains multiple such clusters. Conservative estimates suggest dozens, possibly hundreds. The total mass likely exceeds 10 to the power of 15 times our star's mass. How do you assemble this much mass into a specific pattern? Gravity provides the only mechanism we know that works at these scales. But gravity's influence diminishes with distance. To pull matter together, you need that matter to start reasonably close. For ring formation, you need special initial conditions. The matter must start distributed in a pattern that gravity can then refine into a ring, perhaps a thin shell of slightly enhanced density in the early universe. But what creates the initial shell? Or consider rotational effects. If a massive region of space possessed net angular momentum, it might flatten into a disk as it collapsed gravitationally. We see this happening in smaller systems. Rotating gas clouds form protoplanetary disks around young stars. The problem is timescale. A rotating cloud collapses into a disk relatively quickly once gravity dominates. But the Big Ring spans such vast distances that even light takes over 1 billion years to cross it. Material on opposite sides can't communicate quickly enough to coordinate rotation. Dark matter might help speed things up. Dark matter dominates the mass budget at large scales. It doesn't interact with light or normal matter except through gravity. This means dark matter can collapse faster than normal matter in some circumstances. If dark matter organized itself into a ring pattern first, normal matter might follow. The dark matter ring creates a gravitational template. Gas falls into this template. Stars form from the gas. The visible ring we observe reflects an underlying dark matter structure that formed earlier. But this still requires the dark matter to organize into a ring somehow. We're back to the same question. What creates the ring pattern in the first place? Perhaps multiple processes combine. An initial density fluctuation creates a rough ring shape. Dark matter collapses into this shape quickly. Normal matter follows more slowly. Minor variations get smoothed out over time through gravitational interactions. The math works somewhat better when you combine multiple effects, but it still pushes against the time constraints. 7 billion years to go from tiny density fluctuations to a fully formed billion light-year ring seems barely plausible even with optimistic assumptions. And we haven't even addressed why the ring shape appears at all. Random processes should produce random shapes. The Big Ring's near-perfect symmetry demands explanation beyond statistics. The construction problem highlights a fundamental gap in our understanding. We can describe what exists. We can measure it precisely. But explaining how it came to exist pushes our theoretical frameworks beyond their breaking point. The Big Ring stands as a monument to our ignorance, a cosmic puzzle that resists all attempts at solution. Dark matter plays a complicated role in this story. On one hand, it makes structure formation possible. On the other hand, it limits how large structures can grow. We don't know what dark matter is made of. We've never detected a dark matter particle directly. We know it exists because we observe its gravitational effects. Galaxies rotate too fast for the visible matter they contain. Galaxy clusters hold together despite not having enough visible mass. The leading theory suggests dark matter consists of weakly interacting massive particles. These particles have mass, creating gravitational pull, but they don't interact with light or normal matter except through gravity. Dark matter appears to cluster on all scales. Dark matter halos surround individual galaxies. Larger halos encompass galaxy clusters. The cosmic web consists primarily of dark matter filaments with normal matter concentrated along them. But dark matter also participates in cosmic expansion. Space expands everywhere, including regions filled with dark matter. This expansion works against structure formation. As the universe grows, matter spreads out. Gravity must work harder to pull matter back together. At very large scales, expansion wins. Above certain size limits, structures can't hold themselves together gravitationally. The expansion of space pulls them apart faster than gravity can pull them together. This sets a maximum size for gravitationally bound structures. The theoretical calculations suggest this maximum sits around 1.2 billion light-years. Structures larger than this shouldn't be able to form as coherent objects. The Big Ring violates this limit. At 1.3 billion light-years across, it exceeds the maximum size, yet it clearly exists as a coherent structure. The galaxies within it show correlated positions. They follow a pattern. Maybe the Big Ring isn't gravitationally bound. Perhaps it's not a single structure in the traditional sense. Instead, it could be a chance alignment of smaller structures that happen to form a ring pattern from our viewpoint. But statistical tests argue against this interpretation. The probability of so many galaxies randomly aligning into such a specific pattern is extremely low. The magnesium absorption data shows these galaxies exist at similar distances from us. They genuinely occupy the same region of the universe at the same cosmic time. If the Big Ring is real and coherent, dark matter's role becomes puzzling. The structure must contain enormous amounts of dark matter. Estimates suggest 5 to 10 times more dark matter than normal matter. This dark matter must somehow organize into the ring pattern. Dark matter simulations don't naturally produce rings at these scales. They produce filaments, clusters, voids, web-like patterns. The simulations match observed large-scale structure quite well in most respects, but they don't predict big rings appearing at redshift 0.8. Some cosmologists wonder whether dark matter itself might vary in its properties across different regions of space. If dark matter behaves differently in the region containing the Big Ring and giant arc, that could explain their anomalous formation. However, this hypothesis merely replaces one mystery with another. What would cause dark matter's properties to vary? Let's run the numbers on gravitational timescales. How long does gravity actually need to create large-scale structure? Gravity works through a simple rule. Masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. The larger the masses and the closer together they are, the stronger the attraction. For two galaxies separated by millions of light-years, gravitational attraction is weak. They pull on each other, yes, but the force is tiny compared to the cosmic expansion pushing them apart. Only in regions where matter is already slightly denser does gravity overcome expansion. Start with a region that's 10% denser than average. Gravity pulls in more matter from the edges. The region grows to 20% denser, then 30%. The process accelerates. Eventually, the overdense region collapses into a distinct object. For a galaxy-sized object, this takes perhaps a few 100 million years. For a galaxy cluster, it takes longer. You need multiple galaxies to form first, then gather together. The process extends over 1 to 2 billion years. The Big Ring spans over 1 billion light-years. For gravity to organize matter across this scale, signals must propagate from one side to the other. But gravitational influences propagate at the speed of light. Light takes over 1 billion years to cross the Big Ring's diameter. Think of it this way. Imagine trying to organize a group of people scattered across a city. You can shout instructions, but sound travels slowly. By the time your voice reaches someone 10 blocks away, minutes have passed. Coordination becomes difficult. Now, scale that up to cosmic sizes. Gravitational signals between opposite sides of the Big Ring take over 1 billion years to propagate. During that time, cosmic expansion has pushed everything farther apart. The coordination required to form a coherent ring structure seems nearly impossible. Unless the structure formed differently, Perhaps it didn't build up gradually from small to large. Perhaps something created the overall pattern early, and individual galaxies formed within that pre-existing pattern. Computer simulations test these ideas. Researchers run virtual universes, starting with conditions matching the cosmic microwave background. They let billions of years pass in simulation time, watching how structures form. The best simulations reproduce observed structure remarkably well at small and medium scales. Galaxies form at the right times. Galaxy clusters assemble on correct timescales. The cosmic web emerges naturally. But at the very largest scales, the simulations diverge from observations. Simulated universes don't produce big rings. The largest coherent structures in simulations max out below the theoretical size limits. Yet in the real universe, we observe exactly this. Either we're witnessing an astronomically unlikely coincidence, or our simulations are missing crucial physics. The gravitational timescale problem admits no easy resolution. Every attempt to speed up structure formation through conventional means runs into other constraints. Make dark matter collapse faster, and you create problems with galaxy formation at smaller scales. Increase initial density fluctuations, and the cosmic microwave background should show stronger variations than observed. When one of the founders of modern cosmology questions the standard model, people listen. Jim Peebles won the Nobel Prize in Physics in 2019 for his theoretical discoveries in physical cosmology. He helped develop the Big Bang theory. He predicted the cosmic microwave background. Now, Peebles suggests that ultra-large structures, like the Big Ring, might indicate problems with the lambda CDM model. Lambda CDM represents the standard model of cosmology. Lambda stands for the cosmological constant, dark energy. CDM means cold, dark matter. Lambda CDM works extraordinarily well for most observations. It predicts the cosmic microwave background temperature fluctuations accurately. It explains the abundance of light elements created in the Big Bang. It matches the observed acceleration of cosmic expansion, but Peebles notes that the model might be approximate rather than exact. At very large scales, or in specific conditions, deviations might appear. The Big Ring could represent such a deviation. He doesn't claim to know what modification is needed. He simply observes that anomalies like the Big Ring should prompt us to question our assumptions. This represents a significant acknowledgement. Peebles isn't a fringe scientist proposing radical alternatives. He's a mainstream figure, one of the most respected cosmologists alive. His willingness to entertain modifications to lambda CDM lends credibility to concerns about ultra-large structures. What kinds of modifications might be necessary? Peebles has suggested cosmic strings as one possibility. These hypothetical defects in space-time could organize matter into unusual patterns. Other cosmologists propose different modifications. Perhaps dark energy doesn't have constant density everywhere. Maybe it varies from region to region, affecting structure formation differently in different places. Some suggest the universe isn't as homogeneous as we assume. The cosmological principle might be an approximation that breaks down when examined carefully. Maybe the universe has texture at large scales that current models don't capture. Modifying lambda CDM isn't undertaken lightly. The model has passed countless tests. Any modification must explain everything lambda CDM already explains while also accounting for anomalies like the Big Ring. One possibility is that lambda CDM is perfectly correct for average conditions, but fails to predict rare events. Most of the universe might follow the model precisely, but in unusual locations or circumstances, unexpected structures could emerge. Peebles emphasizes caution. He notes that we could be seeing patterns in noise, finding structure where only randomness exists. We need rigorous statistical methods to distinguish real anomalies from coincidence. But once we've established that anomalies are real, we must take them seriously. The discovery of the Big Ring represents exactly the kind of observation that should drive theoretical development. It challenges existing models. It demands explanation. People's willingness to question lambda CDM carries weight throughout the cosmology community. When younger researchers propose modifications to the standard model, they face skepticism and resistance. When Peebles makes similar suggestions, people listen. His endorsement legitimizes the search for alternatives to lambda CDM. The standard model of cosmology succeeds in spectacular ways. Predictions made decades ago have been confirmed to remarkable precision. The cosmic microwave background temperature matches predictions. The ratio of hydrogen to helium aligns with Big Bang nucleosynthesis calculations. Lambda CDM makes specific predictions about how structure forms. It predicts the statistical properties of galaxy clustering. It forecasts how galaxy distributions vary at different scales. For the most part, observations confirm these predictions. Until they don't. The Big Ring represents a clear deviation. The giant arc represents another. The 7 ultra-large structures collectively suggest that something about structure formation at the very largest scales differs from lambda CDM predictions. Defenders of lambda CDM argue that statistical flukes explain the anomalies. In any large dataset, you'll find outliers. Maybe the Big Ring is simply one of those unlikely events that probability permits. But how unlikely is too unlikely? The Big Ring's statistical significance suggests less than 1 in 10,000 chance of random occurrence. Finding both it and the giant arc in the same region pushes the combined probability much lower. Critics note that lambda CDM contains several components we don't fully understand. Dark energy makes up 68% of the universe's energy budget. We don't know what it is. We model it as a cosmological constant, but maybe dark energy evolves over time or varies from place to place. Dark matter comprises 27%. We've never detected a dark matter particle. We assume it's cold, meaning slow moving. But maybe dark matter has properties we haven't discovered. Normal matter accounts for only 5%. This includes everything we can see: stars, planets, gas, dust. In cosmic terms, normal matter is a trace component. Building a cosmological model on components we don't understand seems risky. Yet, lambda CDM succeeds precisely because it captures the behavior of dark energy and dark matter empirically. We may not know what these things are, but we know how they affect cosmic expansion and structure formation. The Big Ring tests those predictions at their limits. Structure formation at billion light-year scales pushes lambda CDM into regimes where it hasn't been thoroughly validated. Or perhaps we're seeing the first hints of new physics. Every successful theory eventually finds its limits. Newtonian gravity works perfectly for planets orbiting stars, but fails near black holes. Lambda CDM might be similarly limited. Excellent for most purposes, but incomplete. The Big Ring could be pointing us toward whatever comes next in cosmology. The success of lambda CDM at most scales makes its failure at the largest scales more puzzling. A theory that works excellently for 99% of observations but fails for 1% presents a difficult challenge. Do we modify the entire theory to accommodate that 1%? Or do we accept that some observations remain unexplained? The Big Ring forces this question into sharp focus. Cosmologists can no longer ignore the tension between theory and observation at the largest scales. Alexia Lopez didn't discover the Big Ring by accident. She used a clever technique that turned the universe itself into a detection system. Quasars provided the key. A quasar blazes with the light of trillions of stars packed into a region smaller than our solar system. At the center sits a supermassive black hole, millions or billions of times more massive than our star. Matter spiraling into the black hole heats to millions of degrees, radiating across the entire electromagnetic spectrum. This makes quasars among the brightest objects in the universe. We can detect them across billions of light years. Their light serves as a probe of everything between them and us. As quasar light travels through space, it passes through clouds of gas surrounding galaxies. These gas clouds contain various elements, Each element absorbs specific wavelengths of light. By examining which wavelengths get absorbed, astronomers can determine what the light encountered along its journey. Magnesium absorption works particularly well for this technique. Gas halos around galaxies contain abundant magnesium. When quasar light passes through these halos, magnesium atoms absorb light at characteristic wavelengths. The absorption strength indicates how much magnesium the light encountered. The wavelength shift reveals the distance to the gas cloud. Lopez examined spectra from 40,000 quasars. Each spectrum showed multiple absorption features at different wavelengths. Each feature corresponded to a gas cloud at a specific distance. By mapping all these clouds in three-dimensional space, Lopez could trace out where matter concentrated in the universe. Imagine standing in a dark room with 40,000 flashlights positioned at random locations. The flashlight beams illuminate dust particles floating in the air. By noting which beams show dust and at what distances, you can map out the dust distribution. Lopez did the same with cosmic structure. Quasars acted as her flashlights. Gas clouds played the role of dust particles. The absorption lines told her where along each line of sight the gas clouds existed. Combine data from 40,000 lines of sight, and patterns emerged. The Big Ring appeared as a concentration of absorption features arranged in a ring pattern on the sky, all at similar distances from Earth, all showing similar redshifts. The pattern wasn't obvious from any single quasar. Only by combining data from thousands of quasars did the full structure reveal itself. This technique opens new possibilities for detecting large-scale structure. Traditional methods map galaxies directly. This requires enormous amounts of telescope time. The magnesium absorption technique sidesteps this limitation. A single quasar spectrum can reveal dozens of gas clouds at different distances. The method works especially well at high redshifts where direct galaxy surveys struggle. Distant galaxies appear faint and small, but quasars remain bright even at extreme distances. Lopez's discovery demonstrates the power of this approach. She found a structure that might have remained hidden for years using traditional survey methods. The Big Ring doesn't stand out dramatically in direct galaxy observations. Its signal emerges clearly only when you examine absorption patterns in quasar spectra. 9 billion years. That's how long the light from the Big Ring has been traveling to reach us. It departed those distant galaxies when the universe was barely half its current age. The light left when Earth didn't exist. Our solar system hadn't formed yet. The gas and dust that would eventually coalesce into planets still drifted in interstellar space. The Milky Way galaxy looked different, smaller, less organized than today. As the light traveled, space expanded around it. Every second, every year, every million years, the distance between the source and destination grew larger. Because space itself stretched, new space appeared between every pair of points in the universe. This expansion stretched the light's wavelength too. Photons that left the Big Ring in the ultraviolet part of the spectrum shifted into visible light. Visible light shifted into infrared. By the time the light reached Earth, its wavelength had increased by a factor of 1.8. Astronomers measure this stretching as redshift. The amount of redshift tells us how much the universe expanded during the light's journey. Redshift 0.8 means the universe expanded by a factor of 1.8. Think about what this means. We're not seeing the Big Ring as it exists now. We're seeing it as it existed 9 billion years ago. The structure might look completely different today. Galaxies within it have aged. Stars formed and died. Galaxy mergers might have occurred. We have no way to know the Big Ring's current state. The light showing us its present condition won't reach Earth for another 9 billion years. We're looking at ancient history frozen in light. This time, delay applies to everything we observe in space. The farther away something sits, the longer its light takes to reach us, the further back in time we're seeing. The Andromeda Galaxy appears as it was 2.5 million years ago. In effect, Telescopes function as time machines. They let us peer into cosmic history. The deeper we look into space, the further back in time we see. The Big Ring sits partway along this timeline. At redshift 0.8, we're seeing an epoch when galaxies were more actively forming stars, when galaxy mergers happened more frequently, when the cosmic web was still assembling. Studying structures at this distance helps us understand cosmic evolution. We can compare the Big Ring to structures in the nearby universe. We can see how large-scale patterns change over time. The light also carries information about everything it passed through during its journey. Absorption lines reveal not just the Big Ring itself, but intervening gas clouds, galaxy halos, and cosmic web filaments between the Big Ring and Earth. By the time you finish reading this sentence, light from the Big Ring has traveled another 100,000 miles toward Earth. New photons arrive constantly, carrying information from that distant structure's past. We're witnessing ancient cosmic history in real time. This ancient light carries encoded within it the history of cosmic evolution. Every interaction it experienced during its journey left subtle imprints. Careful analysis can extract information about the matter distribution at different epochs. The Big Ring's light provides a window into conditions 9 billion years ago, when the universe looked vastly different than today. Here's an unsettling thought. What if something enormous exists beyond what we can see? Something so massive that its gravity affects even the observable universe? The observable universe represents everything we can possibly see from Earth. It's limited by the speed of light and the age of the universe. Light travels at 300 million meters per second. The universe has existed for 13.8 billion years. That defines a sphere roughly 93 billion light-years across, centered on Earth. But the entire universe extends beyond this sphere, probably far beyond. We just can't see those distant regions because their light hasn't had time to reach us yet. What if massive structures exist in those unseen regions? Structures so large they dwarf even the Big Ring. Their gravitational pull would affect everything, including the portion of the universe we observe. Some astronomers think they've detected exactly this. The cosmic microwave background shows a puzzling feature. When measured in different directions, the temperature appears slightly warmer toward the constellation Aquarius and slightly cooler in the opposite direction. Most cosmologists interpret this motion as our solar system's peculiar velocity. We orbit the Milky Way center. The Milky Way moves through the local group. These nested motions combine to create our overall velocity. But a minority of scientists propose an alternative. Maybe the entire observable universe drifts in a particular direction. Maybe something outside our cosmic horizon pulls on everything we can see. They call this hypothetical external influence the dark flow. Evidence for dark flow remains controversial. Some analyses of galaxy cluster motions suggest they move in coordinated ways across large scales. Other analyses find no such coordinated motion. If dark flow exists, it would profoundly impact cosmology. It would mean our observable universe isn't representative of the whole. The cosmological principle would fail globally. The Big Ring could relate to this scenario. Perhaps structures outside our observable universe created gravitational influences that organized matter into unusual patterns within the regions we can see. This idea seems speculative. We're invoking something we can't observe to explain something we can observe. That's generally poor scientific practice. But conventional explanations struggle with the Big Ring. The possibility of external influences also affects how we interpret the cosmological principle. If the universe extends far beyond what we observe, and if it contains structures at scales comparable to our observable region, then the distribution of matter within our horizon might not be representative. Maybe we're making the same mistake with the universe. The Big Ring and other ultra-large structures might seem like violations of homogeneity only because we're looking at too limited a region. Of course, we can't expand our view beyond the observable universe. That's why it's called observable. Everything beyond remains speculation. The dark flow hypothesis remains deeply controversial because it challenges fundamental assumptions about cosmology. If confirmed, it would suggest that the observable universe represents just one region of a much larger cosmos with potentially different properties elsewhere. Our cosmological models would need radical revision to accommodate such a possibility. The cosmic microwave background holds clues about the universe's earliest moments. This radiation filled space when the universe was only 380,000 years old. We detect this radiation as a faint microwave glow coming from all directions. Its temperature averages 2.725 Kelvin, but tiny fluctuations exist. Some regions appear slightly warmer, others slightly cooler. The variations amount to only 1 part in 100,000, but they're crucial. These temperature fluctuations represent density variations in the early universe. Slightly denser regions appear slightly warmer. Over billions of years, gravity amplified these tiny density differences into the cosmic structure we see today. By studying the cosmic microwave background's fluctuation pattern, we can determine the initial conditions for structure formation. The data shows that the early universe was remarkably smooth. No huge density contrasts. No massive structures already formed. This creates a puzzle. How did the Big Ring form from such smooth initial conditions? The density fluctuations we observe don't seem large enough to create billion light-year structures within 7 billion years. Unless we're missing something. Some researchers suggest the cosmic microwave background might hide additional information. Perhaps certain types of density fluctuations don't show up clearly in the temperature map. Others point to anomalies in the cosmic microwave background itself. The cold spot, an unusually large region of below-average temperature. The axis of evil, an unexpected alignment in the pattern of fluctuations. The hemispherical asymmetry, where one half of the sky shows slightly different statistical properties than the other half. These anomalies might be statistical flukes, or they might indicate something fundamental about the early universe that we don't understand. Could these anomalies relate to the Big Ring? Possibly. If the early universe contained special conditions in certain regions, those regions might produce unusual structures later. But the cosmic microwave background shows us the universe at redshift 1090. The Big Ring exists at redshift 0.8. Vast amounts of cosmic evolution separate these two epochs. Researchers are working on this connection. They run simulations starting from cosmic microwave background conditions and evolving forward in time. They're trying to determine whether any configuration of initial conditions could produce the Big Ring by redshift 0.8. The cosmic microwave background also constrains cosmic string models. If cosmic strings exist and create large-scale structure, they should leave distinctive imprints in the cosmic microwave background pattern. Astronomers have searched for these imprints. Some claim to have found hints, others remain unconvinced. Future observations might help. Future missions might discover subtle patterns that current data misses. Those patterns could explain the Big Ring. Future cosmic microwave background missions might resolve some of these mysteries. Technology improves constantly. Each new generation of instruments detects fainter signals with better precision. Patterns invisible to current telescopes might become clear within a decade. The answers to the Big Ring's origins could be hiding in data we haven't yet collected. The cosmological principle isn't just convenient, it's foundational. Almost every calculation in cosmology assumes the universe is homogeneous and isotropic at large scales. Remove that assumption, and the mathematics becomes vastly more complicated. Einstein's field equations relate the geometry of space-time to the distribution of matter and energy. In a homogeneous, isotropic universe, these equations simplify dramatically. You can describe the entire universe with just a few parameters. Without homogeneity and isotropy, you need different equations for every point in space. The universe becomes a patchwork of regions with different properties. the simple models we use today wouldn't apply. Some cosmologists are exploring inhomogeneous cosmology. They're developing mathematical frameworks that don't assume perfect smoothness. These models are much harder to work with, but they might better describe the actual universe. One idea involves back reaction. In standard cosmology, we treat the universe as smooth and calculate average properties, but the actual universe contains structure, galaxies, clusters, voids. These structures create local variations in space-time curvature. Think of it like averaging road speeds. If you assume all roads are highways with speed limits of 65 miles per hour, you calculate one average. But actual roads include city streets at 30 miles per hour. The real average differs from the simple assumption. Could back reaction explain accelerated expansion without dark energy? Some researchers think so. They argue that the clumpy distribution of matter causes space to expand faster on average than smooth models predict. Most cosmologists remain skeptical. Calculations suggest back reaction effects are too small to explain observed acceleration. But the debate continues. Another implication involves the fundamental constants of nature. We assume physical constants remain the same everywhere. The speed of light, the gravitational constant, all fixed across the universe. But what if they vary slightly from place to place? The Big Ring, if it represents a region with unusual properties, might exhibit slightly different physics than surrounding space. The anthropic principle also enters the discussion. If the universe isn't homogeneous at the largest scales, different regions might have different properties. Perhaps most regions can't support life because their physical constants fall outside the narrow range needed for stars, planets, and chemistry. This reasoning makes many scientists uncomfortable. But if the universe really does vary in its properties across different regions, we must acknowledge that our observations necessarily come from a life-permitting region. The Big Ring challenges us to reconsider our most basic assumptions about the cosmos. Maybe the universe isn't as simple as we hoped. The philosophical implications of abandoning the cosmological principle extend far beyond technical cosmology. If the universe isn't homogeneous at large scales, it raises uncomfortable questions about why we occupy the particular region we do. Are we in a typical region or an atypical one? Can we draw general conclusions about the universe from our limited vantage point? These questions touch on anthropic reasoning and our place in the cosmos. The story of the Big Ring doesn't end here. It's just beginning. Telescopes across the world continue surveying the sky. New instruments come online. The pace of discovery accelerates. The James Webb Space Telescope peers deeper into the universe than ever before. Its infrared vision cuts through dust and distance, revealing galaxies from cosmic dawn. Every image contains potential surprises. The Vera Rubin Observatory in Chile will soon begin operations. It will photograph the entire visible sky every few nights. Over 10 years, it will detect billions of galaxies and catalogue their positions. This massive dataset will reveal large-scale structure in unprecedented detail. The European Space Agency's Euclid mission maps the cosmic web across billions of light-years. Its data will test the cosmological principle rigorously. If structures like the Big Ring are common, Euclid will find them. Ground-based surveys continue improving. The Sloan Digital Sky Survey keeps expanding. Quasar catalogues grow. Each edition increases the chance of finding more ultra-large structures. The technique Lopez pioneered will likely discover more rings, more arcs, more unexpected patterns. She's continuing her research, analyzing additional regions of sky. Other astronomers are adopting her methods. What will we find? More ultra-large structures, almost certainly. Perhaps structures even larger than the Big Ring and Giant Arc. Perhaps entire networks of connected rings and arcs. Each discovery will further test the cosmological principle. At some point, the accumulation of evidence will demand theoretical revision. We can't keep calling structures impossible while finding them repeatedly. New theories are already being developed. Modified gravity frameworks, alternative dark matter models, inhomogeneous cosmology approaches. Some will prove wrong, others might capture important insights. This represents science at its finest. Observations challenge theory. Theory adapts to accommodate observations. New predictions emerge. More observations test those predictions. The cycle continues. The Big Ring reminds us how much we still don't know. After decades of cosmological progress, we still encounter phenomena that surprise us. The universe still holds secrets. Maybe in a few years, the Big Ring will seem less mysterious. We'll have found dozens of similar structures. We'll have developed theories explaining their formation. They'll fit comfortably into an updated cosmological framework. Or maybe the mystery will deepen. Maybe each new structure will raise more questions than answers. Maybe we're witnessing the first cracks in a theoretical edifice that will eventually need rebuilding from the foundation up. Either way, the journey continues. Astronomers point their instruments at the sky. Data accumulates. Patterns emerge. Questions multiply. The ring hangs in space 9 billion light-years away, unchanged by our observations, indifferent to our theories, simply existing in defiance of our expectations. It waits for us to understand. We just have to learn how to read it. The ring hangs in space 9 billion light-years away, unchanged by our observations, indifferent to our theories, simply existing in defiance of our expectations. It waits for us to understand. The clock is ticking. New data arrives daily. The answer is out there, somewhere in the darkness between galaxies, written in patterns of light that crossed the universe to reach our eyes. We just have to learn how to read it. Every telescope pointed skyward brings us closer to that understanding.